For topic two, we're going to talk about measuring angles. So I already told you in the previous video that you have an initial side and you have a terminal side. And basically think of them kind of laying on top of each other. And then you sweep open the terminal side in either the positive or the negative direction. So positive would be counterclockwise, negative would be clockwise. Once you figure out where that terminal side ends, there's a space between those. Like how far did we go from the initial side to the terminal side? That's how we measure angles. So we need to talk about measuring angles, just kind of a brief introduction to it in topic two. So first of all, we do have an angle. We generally denote them with theta. So that's the symbol for theta, one of the Greek letters. And an angle theta can be measured in degrees or radians. So we're going to talk about radians much later in this section. For now, we're going to focus on just degrees, okay? So degrees are a way to measure angles. A lot of times we're already kind of familiar with the idea of measuring portions of a circle. So we know a circle has a certain number of degrees that can measure that. Same idea, exact same idea here. So when an angle theta is in standard position, we know that from the previous video, with the terminal side on the X or Y axis, we say that theta is a quadrantal angle. Now, I will be honest with you, I don't think I have ever in my life called these a quadrantal angle. I've always just called them quadrant angles. So you'll hear me refer to them as quadrant angles. So before we get into measuring like sort of specific angles, let's just understand what these quadrant angles are, because it'll give us kind of an idea of the different, I'm stuttering, the different sizes of angles that you can see. So these quadrant angles, the terminal side is always going to land on the positive or negative X or Y axis, okay? So let's go ahead and start drawing these angles. Let's do them in red. Okay, so example two says draw each quadrant angle. And this is just to kind of define what these quadrant angles are so you understand what they are, okay? So we want these to be in standard position. So the vertex is going to be at the origin. And then we want the initial side to be the positive x-axis. Doggone it. Okay. Now, if you have a 0-degree angle, that means the terminal side never sweeps out. Positive or negative, it just never sweeps out. So it's almost as if the terminal side is laying on top of the initial side and it never opens. It never sweeps out, okay? So this right here, like it or not, this is a 0-degree angle. We never sweep open, okay? Now, a 90-degree angle, a lot of people are familiar with a 90-degree angle because when you first start talking about geometry, you'll talk about right angles or right triangles. And a right angle is an angle that measures exactly 90 degrees. And we know, kind of we're familiar with this idea, that a 90-degree angle is like the perfect corner of a rectangle. So if I have my origin as the vertex, the positive x-axis is my initial side. Because we're looking at positive 90 degrees, we're going to sweep open in the counterclockwise direction. And we're going to sweep open to exactly the positive y-axis. This is exactly 90 degrees. Okay, so 90 degrees falls exactly on the positive y-axis. Another way that you've probably seen this before is you could see an angle like this. And instead of like labeling it 90 degrees, they'll put a little box in the corner. That box indicates 90 degrees. So you've probably seen that at some point. If you haven't, you'll definitely see it soon. Okay. So next up, we have 180 degrees. Some people refer to this as a straight angle. So again, we have our vertex at the origin, the initial side at the positive x-axis, and we're going to sweep open in the counterclockwise direction. So we sweep, we get to 90 degrees, and then to go 90 more, we're going to go all the way to the negative x-axis. That is 180 degrees, and that's going to be really important. We're actually going to talk about 180 degrees later in this worksheet. Okay, so that's a straight angle. So from the initial side to the terminal side, you just go all the way to the negative x-axis. All right, 270 degrees is 90 more than 180. So we have our initial side on the positive x-axis. We have the vertex at the origin. We're going to open in the counterclockwise direction. So we go 90 degrees, 180, 90 more puts me right here at the negative y-axis. Okay? Now, finally, we get 360 degrees. 360 degrees is 90 more than 270. So we have our vertex at the origin. Initial side is the positive x-axis. We start opening in the counterclockwise direction. So we go 90, 180, 270, and 360. Doggone it. I hate when Microsoft does that to me. There. That's not as pretty. So we end up doing a full revolution. So if we go from the initial side all the way around to where the terminal side is right back at the initial side, we have 360 degrees. Now, the angle looks very much like 0 degrees because you just have the initial side and the terminal side kind of like lying on top of each other. But make note of the direction. That little spiral means something. It means we did one full revolution. Okay. And also notice a lot of times you learn about degrees when you start talking about circles in a geometry class. If we can imagine the end of this angle kind of sweeping around, it's making a circle. So one full revolution is 360 degrees, which ends up making a circle. So that's why a circle is a full 360 degrees. So you have 0 revolution, that's 0 degrees. You have a quarter of a revolution, that's 90 degrees. A half a revolution, 180 degrees. 3/4 of a revolution is 270 degrees. And one full revolution is 360 degrees. So those are your quadrant angles. They are very important. We're going to talk about them in a future section. We're going to start forming something called a unit circle, and these quadrant angles become part of that. Okay. Now for the next example, example 2, we're going to start measuring angles that fall in between those quadrant angles. Okay. So example 3 says determine how much of a revolution is completed by each angle and then draw the angle described in standard position. Okay, so for part A, we have positive 135 degrees. So when we're asked to determine how much of a revolution is completed, what we want to do is we want to compare 135 degrees to 360 degrees. What fraction of a rotation has been completed? So we're going to look at, let me go back to black, 135 degrees, and we're going to compare it to 360 degrees. Now, if you're really good at simplifying fractions, you could simplify this fraction by hand. Me, I'm going to save a little time and energy, and I'm going to use my calculator. Okay? So go to, ooh, do I have it up? I think that's it. That is definitely not it. So stop that share. Hold on. Let me find my calculator. There it is. Okay, so there's my calculator. I will tell you right now, I don't love my calculator setup, but we use the technology we have and we're grateful for it, okay? So we were looking at 135 degrees compared to 360 degrees. So you could just take 135, divide it by 360, and it's going to give you a decimal answer. So we're like 0.375, that's not super helpful. You're right. If we could get this in fraction form, it is super helpful. So if you see these two colorful buttons on your calculator, below that you have the math button. That's going to pull up a series of menus. The first menu is the math menu, and we're very interested in option 1. This like little arrow with a fraction, it'll turn a decimal into a fraction. So we're going to choose option 1. The calculator is going to be like, are you sure? And you're going to say, absolutely. So we now convert that to 3/8. So we know that 135 degrees is 3/8 of a full revolution. Now, there's another way to type in a fraction into your calculator. So you see this green alpha button, you click alpha and then you go y equals. There's a couple of ways to make this happen, but I think this is the most general way that works for most calculators. So you go alpha, y equals, it pulls up a fraction menu. And so we're going to choose option 1. And so basically this just creates a template where you can type in your fraction, which is sometimes easier for students. So the numerator, 135, the denominator, 360. And when you hit enter, it's automatically going to have it in fraction form. So that's kind of nice. So 3/8 of a revolution. So let's go back to the worksheet. And there it is. All right, so we now know that 135 degrees is 3/8 of a revolution. So if we take this Cartesian plane and split it into 8 equal size regions, we could just count off 3 of those, and that'll show us what 135 degrees is. So let's start with the positive x-axis. That's going to be our first region. And then we're going to go halfway between that and 90 degrees. So that's 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, and then we're back to 8/8. Okay, so that splits this Cartesian plane into 8 equal size pieces. That ends up being one full revolution as 8 pieces. And then we're going to start to draw our angle. So vertex at the origin, initial side, positive x-axis, and then we're going to count off 3 of those 8s. So in the counterclockwise direction, we're going to go 1, 2, 3. So this is approximately 135 degrees. Okay? Now let's look at part B. So for part B, we have 120 degrees. So we need to compare 120 degrees to 360. I will tell you that this is technically, or well, it's not technically, it's just flat out negative 120 degrees. So when we draw the angle, the negative tells us which direction we need to draw it. Now 120 degrees compared to 360, I hope a lot of you can do this in your head, but if not, we jump over to the calculator. I'm going to go ahead and go alpha y equals and then numerator 120, denominator 360. Hopefully a lot of you know this is just 1/3, but if not, the calculator will tell you. So 120 degrees is 1/3 of a revolution. So let's see what that's going to look like. So if we were going to split this Cartesian plane into thirds, we would have a third kind of like here. Well, you don't need the arrow. And a third kind of like here, and then here. So those are our thirds approximately. Okay. Now we're going to draw our angle. So we want the vertex at the origin. Positive x-axis is the initial side, and because this is negative 120, we need to open in the clockwise direction. So we want to open this away, and that's approximately 120 degrees. Okay? Negative 120 degrees. Don't forget your negative. Now, finally, we have 405 degrees, so we're going to compare 405 degrees to 360. So let's jump over to the calculator. It is helpful if you can get to the point where you just kind of can, sort of, I don't want to say eyeball, but sort of eyeball some of these measures so you don't always have to like draw the Cartesian plane and split it into equal pieces, but just know that you always can if you need to. So alpha y equals, we're comparing 405 degrees to one full revolution, which is 360. We hit enter, and we get that this is 9/8 of a revolution. So let's draw that. So we're already kind of familiar with eighths. If we look at the Cartesian plane, it's naturally split into fourths. So split each fourth in half. So 1/8, 2/8, 3/8, 4/8, 5, 6, 7, and 8. Now we want a positive angle, so we're going to start with our vertex and our initial side, and then we're going to sweep open in the counterclockwise direction. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, and then doggone it, I hate when it does that. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, and then 9. And that puts us right here. So this is 405 degrees. Notice it's more than one full revolution, and that should make sense because 405 degrees is certainly more than one full revolution. So again, it's nice if you can kind of familiarize yourself with what some of these angles are, because there's going to be some angles that show up quite a bit. But if you ever are stuck, figure out how much of a revolution has been completed, split your Cartesian plane in that many pieces, and then just start counting off. Okay, so that's it for measuring angles. Next up, we're going to talk about partial degrees.